Okay, right, take two. Let's see if this works a little bit better this time. It decided to kick me off for some reason. Make sure I'm live again. Yeah, how weird. Am I? Okay, well, sorry about that. Let's try again. So we have some binomial thing, yeah? Expand this one up. So we want it up to x cubed. We have an integer, so it's just going to be the kind of standard expansion. So x cubed, what we're going to have? We're going to have 2x to the 0, 2x to the 1, 2x to the 2, and 2x to the 3. Let's move that one across a little bit. We have a 1 at the front, so no need to worry about that really, because it's going to be like 1 to the 12, 1 to the 11, 1 to the 10, 1 to the 9, but that's always just 1. And then we need the choose bit, so we're going to have 12 choose 0 is always just going to be 1, and then this one will be 12 choose 1, which is 12. And then we're going to need 12 choose 2, not negative, 12 choose 2, which is 66, and then 12 choose 3, which is 220. Add all of these together. What we're going to get? Well, the first one is always just 1. The second one, 2 times 12 is 24. Now we have 4 times 66, which is 264. And then 220 times by 8. What do we get? 1760. Looks good to me. Now then, super value for x, we want to find the value of this one. So what you can see, like, we want to match the inside up. So 1 plus 2x is 1.02. So x itself is going to be 0.01. So that is good. Let's plug this off in then. What we're going to get? Well, 1 plus 24 and 100, so 0.24. Basically, this is always going to shift by 2 decimal places for every power. So this is going to shift us by 4. So it's going to be plus 0.0264. And then this one as well, plus 0.00160. You see like 2 decimal places, and then we start counting. This is the 4th, we start counting from here, we start counting from the 6th. Add them all up. So what do we have? 1 plus 0.24 plus 0.0264 plus 0.001760. What does that give us? We have 1.27816. And now then, yeah, let's have a look. What is the actual value? I get so 1.02 to the 12, 1.268. All the digits, okay. 268, 24, 1795. Percentage error then, we're going to find the difference in that. So if we take that away, 1.27816, we get some number, and then we're going to divide that by the actual value, 1.02 to the power 12, and then times that by 100. So I get the percentage error of 0.78%. Oh, 36 figs, 782%. Lovely jubbly. The circle one, yeah, I'll go back. So it's going to be a little bit weird, I think. I don't think you'll get one quite like this in the exam. This seems a little bit too far-fetched, do you mean? Unless it's going to be the very last one. So we've got these 2 points. What we want to do is find like a general equation for the tangent. So we differentiate with x squared for 2x. The y squared will become 2y dy dx minus 10 plus 4. Plus 4 dy dx. That should be a 4 in there. And the 0 goes away, 20 goes away. So that will equal 0. If we rearrange for the dy dx, so if we move the 10 and the 2x across, we'll have 10 minus 2x. Factorising this stuff, we'll have 2y and a 4. So that all is dy dx. Divide everything off a little bit, divide by 2, yeah. So 5 minus x, y plus 2. That is our dy dx. Let me move this over a little bit. So what we have, every single equation to our, every one of these green lines, that's going to be true. But that's only when that's the point on the circle. So it has to be one of these two. So we need to like have this to be a different one. But I think it's still going to fit, surely. See, I don't think you've seen one like this in the exam. This is going to be a little bit too tricky. These are from before, like 2017. So a little bit more tricky in some versions. But we have this now. So what's the general kind of shape of this one? Is going to be y minus some y value, y0, is equal, y minus that, sorry, is equal to m. So it's going to be this thing, but with, again, x0 and y0. And that's going to have x minus x0. So where x0 and y0 is some point on the circle. So I think this feels a little bit too far-fetched to have that. Then you want to make sure that this is going to be 4 and 4 for the general x and y. And then it should, you have like two equations. Do you know what I mean? You have a simultaneous equation between this and the circle. So let's see what pops out. We're going to have 4 minus y0 is equal to 5 minus x0 over y0 plus 2. And that's going to be x minus, 4 minus this. I might be overcomplicating this. There might be some simpler way I can do it, but not one I can see off the top of my head. We're just thinking like you want to find the difference between 4 and one of these points. But you can't just do the difference because it's like hidden inside the square stuff, do you mean? Unless we can just do it from this, maybe. Yeah, maybe we do it from that. Maybe I'm overcomplicating this. Let's have another little go. So we're just going to do like, we have 4, 4, and we have this, but it's making sure it's a tangent is the issue. Like making sure that is a tangent. Let's do it a different way, maybe. Can we have just like what points they're going to be? So we know that line has a length of 3. This line has a length of 3. And then these two should be symmetrical. Everything's symmetrical here. Okay, maybe there's, yeah. Ooh, this looks good, doesn't it? So this is symmetrical. And we know this is 0.44. Okay, I was overcomplicating that. This is going to be where was it? 5 minus 2? 5 minus 2. So now we've got that. We can work out that distance. So what is that going to be? Well, it's the distance between the x coordinates. This is minus 4, by the way, for the x. Is 9, yeah? And the distance between the y coordinates is 6. So how far away, like what distance is that going to be? So square root of 9 is 81, plus the 36. Square root of that thing, 3 root 13. So that's that middle length. We know this is 3, and we know that's a right angle. Okay, yeah. So let's draw kind of one of that top triangle we have. We've got this bit going across. We've got the 3 coming down. It's a tangent to the circle, so that is a right angle. We know that length. Yeah, I was overcorrecting the other version. This then 3 root 13. What we have on the right hand side is going to be the 3. That 3 root 13, when we square it, was 117. Yeah, 117. So what we have is like 117 from the bottom is equal to 9 from the 3 plus x squared, the distance we're looking for. So what does that give us? It's going to be 117.9 square rooted. So yeah, 6 root 3. And again, that's a very nice answer. So that does seem pretty good. I think what I was doing is just way overkill. Do you know what I mean? I think I was doing it then for like you could plug in any point and you'd be fine, like where I was doing this stuff. So a bit overkill. So on these ones, yeah, if you can try and do some geometry, it's not too bad of a thing. And knowing like that's a right angle really helps. So trying to spot triangles is always going to be useful. Anything else? Connected rates of change. Yeah, we can do connected rates of change. Let's see if we've got any. What's going to pop up in here? No. This isn't rates of change. This is connected things. Do you know what I mean? But we haven't got any like rate. This is still like designing the packet. You're not talking about like putting things in the packet. What one of those with a shape? Let's see if we can see like, can we see one with one of these like shapes that you get? If not, I'll go and find another one. Like, is that going to be it? No rate again. Do you mean no time? If you find me doing one of those, let me know. If not, I'll go and find one of these. Yeah, connect the rates of change. No, we'll just go and find one. Let's load this up. So A-level maths. Connected rates of change. Yeah, nice. What have we got to go in there? Yeah, we'll whack this in the book. Oh, have a little go. Ooh. So in general, you're going to get given like a few bits of information. If you're unsure, look at the units. So we have diameter is 6, they told us in there. And then we've got a little bits here. So we've got like constant rate of this and this as well. Look at both the units though, meters cubed per minute. So both of those are going to be dV, volume, for the meters cubed, per time. for the minutes, yeah. We've got it's flowing into the tank at this rate, 0.48 pi. If I can write that a bit neater. 0.48 pi. And then it's flowing out of the tank at that leaves the tank, 0.6 pi h. Let me move this over a little bit. So you can always use your limits and your units to find how that's going to be set up. We're then pretty much always going to be told something else later on, like about some measurement for the volume or something. So like here we have the diameter, do you know what I mean? But what we can say then as well, we have volume, height, and time. They're the three units we're thinking about. Volume, height, time. Here we have a relationship without volume. Here we have one with volume. So we need to eliminate volume and replace it with height, basically, yeah? To do that, we'll need the general formula for a cylinder. So V is equal to the volume of a cylinder, yeah? But only of the liquid, not of the entire height. So pi r squared for the bottom. So r is going to be 3, so 9 pi, yeah? Times by the h. And now if we do dv dh, so we've got like 9 pi times the h. Get rid of that. Leaves us with 9 pi. So if we take this thing and kind of mix these all together, I'm going to start with the thing that I want. So I want dh dt. And how can we expand that out? Well, I'm going to have a dh on the top and a dt on the bottom. What's the other variable I have? V. So that's going to go in between. And then we can see that like this bit is what we found up there from the information in there. And then this bit is going to be the reciprocal of that. So as we do this, yeah, the reciprocal, 1 over 9 pi. And then times by all of that stuff above. So the 0.48 pi minus 0.6 pi h. From there then, I'm going to factorize out 0.12 pi. So think 48 and 60, both multiples of 12. So we'll take that out the front. Pi's go. I've got a pi down there. I've got, do that in blue. Pi there, pi there, pi there. It's pi's everywhere, and now there's no pi's anywhere. So what do we have? It's going to be 0.12 on 9, and then lots of all this stuff. There's 4 of them there, 5 of them there. So I've got 4 minus 5h. So by factorizing, what you can see is that that bracket's appeared. So if you can factorize, always factorize. And then this number ends up being 1 over 75. So that's equal to that. And therefore we're done. We times by 75, and you get 75 dh dt is equal to the 4 minus 5h. Lovely jubbly. Yeah, lovely. So now then, we have some equation. You can use this and just go and find something called the general solution. So the one with the constant still in there, like the plus c, you haven't figured out what that is yet. But here they give you some point. So from that we can find the particular solution. So let's find the general first. It's a differential equation. You only have one way of solving it. We have to separate the variables. So all my h's are going to go to the dh side. All my t's to the dt side. What h's have I got? I've got this 4 over 5, 4 minus 5h. So 4 minus 5h in there. We'll integrate that. The 75 you can do with what you like. This thing is going to be one of these log integrals, where if we have a fraction and you have the function on the bottom and the derivative on top, that ends up becoming the natural log of that function. It should be modulus, but you seldom need it in exams in like the A level, so you can mostly just think of it as being like it's just the log of that thing. But it really is the modulus, but yeah, we won't really use that too often. So what does that mean for us here? Well, if we differentiate that, we get minus 5. So it would be really nice if I had minus 5 on the top there. I have a 75, so I can like dismantle this. Part of it has made that. What have I got left over? Minus 15. And the right hand side is just the dt. There's no t's at all. So by choosing where we put our bits, this is then already done. It's already in this format. And now that entire integral is just going to be the log of 4 minus 5h. And that minus 15 is the coefficient of it. T on the right, plus a c. With the c stuff, like I've got logs, so I'm just going to make this log of c. Make my life a little bit easier later on. So this would be called the general solution. because it's true, but we don't know exactly where it is yet. So it's like a family of curves with the shape of it. Like if you were to draw these out and allow C to vary, you'd get some shape, and they'd all kind of like line up like this. Do you know what I mean? They wouldn't cross over. I don't think they ever cross over. Maybe they do cross over sometimes, but at the top of my head, they don't ever cross over. And then like the point you get, like we've been given like whatever it's 0.2, would put you on like this line, and then you know that this one is the correct one that you want for that particular solution. So let's do that now. We have this thing. We want to plug in t is 0, h is 0.2. So doing that, what do we get? We'll have minus 15 log of, well, this is 0.2, times that by 5, it's 1. 4 take 1 is a 3. T is 0, and this will just be log C. So what we can see is that the log C itself is just this. So in this case, we didn't actually need the log C. We could have just called it C. That would be fine. Oh, that should be equals in the middle, sorry. Yeah, we didn't need to call it log C in this case, but it's not so bad. Like that thing's done. We don't need to find C. We wanted to find something to replace that with. It's just in certain cases, what we're going to do is like rearrange this actually first for H. And then in that case, it'll be a little bit easier to think about. So C is actually like 3 to the minus 15, which is a very, very small number. But yeah, that should be fine. Value of T when H is 0.5. So you can see why I didn't rearrange for H. We never actually need to find a value for H. So there's no point in us rearranging this equation for H. If we just take this one, rearrange it for T, what do we get? Well, it's going to be all the stuff we had on the left-hand side originally, the minus 15, 4 minus 5H. And then we would take this away, yeah? We'd have a minus log C on that side. So if we negate all of those bits, it's like I'm going to add on 15 log 3. And here I'm going to combine these all together. So it's like I've got 15 log of 3 over 4 minus 5H. Now then, T when H is 0.5, let's plug that in. So half of 5 is 2.5. So I've got 1.5 in the bottom. 3 over 1.5 is 2. So this should be 15 log 2. Again, answer being so nice is good. What they did on the paper 1, maybe if you get bad answers, don't be too concerned by that. But yeah, this looks okay. This looks all fine by me. Again, method should be right. I might make some number errors along the way, but like the techniques we're doing to solve it should be the right sort of stuff. So like I say, any questions, whack them in the chat. If not, I'll keep doing some random bits. We'll do maybe one more of these. Where's that weird? Yeah, this weird one. So this, I want to show you this thing because it's a little bit strange. Method to start with is normal. Do you know what I mean? It's all the same sort of general idea. We want to find the volume of something. Volume of a cone is, well, it's like a cylinder, pi r squared h. And then we're going to have to times that by a third. Whenever you have like a prism, that would be like the same shape, but it kind of like spirals, not spirals, but like condenses down to a point, you have a third of the original object. So, show that V is equal to this. This is where the tricky bit comes in, because you need generally some other relationship between things. And what they've done is use this triangle and this triangle, the fact that they are similar shapes, because they have the same angle down here, the same angle up there, and this is a right angle. So what we have, we can think about doing sine of both, because we're going to have the, is it sine? No, sorry, tan of both. So tan of both of them will be the opposite over the adjacent. So 16 over 24, which is 2/3, yeah? And that will be the same inside here, so r over h. So sometimes, like if you think about this one, we got a relationship by knowing the, where is it? The general volume, yeah, the formula for just the volume of a cylinder. Here we need a little bit extra to like actually link them together using that. So normally they might give you like the value of it is 10, or like one of the numbers you know. But here we got a relationship by just like spotting that they were similar shapes with that triangle. So we can rearrange this. What's it going to be? 3r is 2h. And now we want to get volume without the r in it. So actually let's get r by itself. So r is going to be 2h on 3. We'll take that, plug it in there. What we're going to get? So it's going to be a third. If we square that thing on the top, we get 4h squared. On the bottom we square it, we get a 9. Times by another h. So what do we have? 4 on the top. H squared, h cubed on the top. And a 27 on the bottom. Oh, my pi. Where's my pi gone? Oh, yeah, I should have just had a pi. There should just be a pi in there, yeah. Pi. Pi. Lovely, jubbly. So, yeah, a bit sneaky. So do spot like, oh, if they've given you these bits and it's the same, it's just a similar shape, not something you thought about at all in A-level, yeah? but it's something that is still valid. Anything from GCSE, will still be questionable in this. Whether they're going to do it or not, different question. But like they could ask you about circle theorems, for example. Hopefully they don't, but it is in there. Do you mean? So let's do the rest of this. What's going on? So now, yeah, water flows into the container at this rate. What are those units? I've got volume, I've got time, and I've got 8. So we know that. We know this. We want to find rate of change when h is 12. So what can we say? Well, we need to find... I feel like I'm missing something. Oh no. V is equal to that. V is that. The rate of change of h when h is 12. Okay, so what we wanted to find is dh dt, yeah? So, same as last time, let's expand it out. We're going to have dh and a dt. What's the other letter we have? A v. What bits do we know? Well, the dv dt we got told is 8, yeah? That's in the question. And we can get a dv dh from this one. So you're always going to get like one of these differentials you just get given, and one you have to actually differentiate to get it out. So differentiate this quick. What we're going to get, dv dh. We'll bring a 3 down. 3 over 27 is a ninth, so it's going to be 4 ninths of pi still there, and now we have h squared. So we can sub that little bit in, but spotting again, dv dh, this is dh dv, so we need to do the reciprocal. So it's going to be like 9 on 4, well, do the whole thing, 9 over 4 pi h squared. Not very good 4. And the dv dt, that was just 8, yeah? So altogether, we can like 8 over 4 is 2, yeah? So 9 times 2, 18. 18 on pi h squared. Plug in the value of 12, what we're going to get, we're going to have dh dt evaluated when h is 12. What's 12? 12 squared, well, 18 over 12 squared is 1/8. So it's 1 over 8 pi. Looks good to me. It's flowing in it so much, and it kind of makes sense. Like the taller you get, it should be that you're not changing the height that quick anymore. The volume being poured in is the same, but obviously like every little like cylinder that we have, imagine like a very little cylinder, like just one that high. Do you know what I mean? Every one of those that we fill in, the next one is bigger, and the next one is bigger, and the next one is bigger. So we should have kind of a low amount of height change towards the end. Think about how much rain there is that's falling, but the sea don't go up much, does it? Sea rise don't rise every time it rains and falls that much. It's all about the tides, not the actual amount of fall, because there's such a big volume of it. It's just not going to affect the height that much at all. So this looks good. Any other questions? When to identify it? So just look at the units. What units do you have? So if we think in here, they told us cubic centimeters per second. So that is going to be dv dt. It's volume and it's time. So it must be that way around. The units are always matched. I mean, they're always going to tell you what the units are. So you can always use that to figure out which thing it's talking about. So hopefully that's not... yeah, there's no other really way to view it. You then just have to think about what 3 things are you talking about. Time's always one of them. Often it's going to be height and volume, or like radius and surface area. Do you mean something like that? You're talking about 2 physical things where you'll have some relationship from the object, i.e. we had volume and height of a cone relationship, and the radius, where you're going to use that, or you get given some value or some relationship with this to eliminate one of them. So we got rid of r, and now we're just working with v, h, and t. So you always generally start with 4. You get given some relationship to eliminate it. So same thing on, like, if you look at this one, we're going to guess at some point we have, like, we get given again, so this is going to be area per second, yeah, dAd time. And we probably will get some value at some point. So you can see here, we're not actually working out like in the last question, we solved for h, yeah? We just got an equation, we solved the differential equation. And these two, we haven't been. Difference being is like we need to have a little bit more information to actually get the formula for it. So are we going to have it here? No, it doesn't look like it. But we can have a look at some more of these. Unless there's any other questions you have. What have you got? Have you approximate values for the trapezium rule? So trapezium rule, you just plug in the values It seems really weird, but like trapezium 4, there is nothing strange going on. We get another little page. Say we have something kind of horrendous. That's not right in white. Oh no, that's fine. Say we have something horrendous, like we've got y is equal to x sine x squared or something like that, and we want to do the trapezium rule on it. What are we going to do? Let's do it between 0 and pi or something. We'll do 0 and root pi maybe. So doing that, we're going to have some shape. I don't know exactly the shape of this, but it's going to be like something like that, I'm guessing. And we can make trapeziums from that. So like boff, 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 and boff. Where if this is root pi, but we'll make it, let's just make it 1. How many of these have we got? 1, 2, 3, 4, 5. So each of those is 0.2, yeah? That's 0.2, this is 0.4, 0.6, 0.8. They might give you a table to fill in, but that's effectively what you want. You want all the x coordinates, 0.2, 0.4, 0.6, 0.6, 0.8, and 1 at the end as well. You do want the 0 also. So at the very end points. And then you're just going to take all the y values, go and find those, whatever they are. I'm going to make these numbers up. These are not necessarily what thing this is. But let's say we have like, I don't know, 0.4, and then we have 0.5 and 0.55, 0.6, and then back down to like 0.1. We have that formula. So you need to add the first and the last, and then 2 times all the other ones. And then we're going to take that and divide times it by half of that width. So this is just the formula of trapezium. Every single one, a plus b over 2 times by the h. H over 2 is there. These are all the a plus b's. Everything on the inside was in 2 trapeziums. Because if you look at this line, I'm in that trapezium, and I'm in this one. So it gets counted twice. But the one on the outside, they don't get counted twice. So you then just take all of these numbers, plug it in this formula, and see what it pops out to be. The over and underestimate stuff, if we look at this, like this graph, we can see our curve is going to be like slightly above, even though not just from my drawing, but because we're falling that way. If we draw one long line, you can see like I'm definitely below it, yeah. So our estimate here is an underestimate. We're underneath the curve the entire time. Why is that true? Because it is, I don't know if it's concave or convex, which whatever the word it is, but because the second derivative is negative, our graph's falling down, yeah, it's falling down. So in that case, you can see like we're kind of circling over the top of it, and like we're too high. The other way around, we'd be doing this, and we'd be having like our trapeziums would join up like that, and you'd have all this extra bit that we counted. So that would be an overestimate. But here, this is going to be an underestimate. And that's it for trapezium rule. There's not really anything else to think about. Get your y coordinates, plug them into this formula, and then just think about, is it an under or overestimate at the end? So if you need to do like percentage error, we just take whatever value you get, and then find the difference between this and the actual one, and divide it by the actual one times by 100 to get it in terms of percent. Any other questions? Hopefully trapezium rule is quite straightforward. There's nothing to really think about almost. If you could just be given the formula and plug in the numbers without having any idea of what it means, and you should be able to just get it to pop out the other side. Any other questions about things? Anything we can think of? If not, I'll just go back to doing some of these random ones. I'll do one more rates of change. We'll do this little circle one down here. So area is increasing at a constant rate of 1.5. So we're going to have dA dt. Get my pen the right side. dA dt is going to be 1.5 or 3 over 2. And we're going to find the rate at which the radius is increasing when the area is 2. So what we want to find is dr dt evaluated when the area is 2. So as always, we have area, we have radius, we have time. We need some relationship, ideally between the two physical ones. So area of a circle is pi r squared. So that's going to tell us that dA dr is 2 pi r. Now then, we can take this dr dt. What we want to find is going to be, well, let's just think dr dt for a sec. Again, dr on the top, dt on the bottom there. What was the other variable we had? A. That's going to be dA. That will be dA. We were told that, which is that bit, we've just figured out what this thing is upside down. So we can plug these values in. What do we have? 1 over 2 pi r times by the 3 over 2. So it's going to be 3 over 4 pi r. We don't have the area of the circle, the radius, we have the area. But what we can say, 2 is equal to pi r squared. So rearranging, we'll have 2 over pi, all square rooted will be r. So we can plug that in here. If we flip it, it's 1 over r in it, yeah. So it's going to be 3 over 4 pi times by pi over 2 square rooted. Probably ways you can rewrite that a bit neater. Do you know what I mean? Like you've got a root pi and a root pi. So I think, yeah, this is the same as 3 over 4 lots of 2 pi square rooted, I think. So you've got pi to the half and a pi on the bottom. So altogether pi to the minus a half, yeah. That looks good. That all looks fine by me. Vectors, yeah, we can do some vectors. Vectors is something that's what I did at uni. Vector calculus was the bit of undergraduate, not what I'm doing at masters, but it was the undergraduate stuff. There was there one at the right at the start? I can't remember. If not, I'll go and find one. If not, I know which one I should find. There was a good. Where was it? I was typing on A-star questions. Was in here? Yeah. Not that. Not that one. Yeah, this little bastard. Oh, come on. Education should always be free, not these barriers in the way. Yeah, get out of my way. So this is what we want. Let's grab it, put it in the book. Get rid of all these other bits of faff we don't want. Looks good.